Did start some of this in class together. I'm going to take you through the beginning again so you have access to anything that you still need clarification on. And then the end of this will be some of the new information that applies to circuits. So the very first thing we talked about was potential difference, or the voltage, or the EMF. Right? So remember, we're looking at a battery. We have a series of chemical reactions that occur. This creates our potential difference between the positive and negative pole of that battery. Our maximum potential difference is called the electromotive force, or the EMF. Here's our basic circuit. Remember, the three things you need to build a basic circuit is a source of energy, or potential difference, a closed path, and some device that uses the energy, some resistance. The other thing we did talk about was how electricity is symbolic of fluids. So for some people, thinking about the flow of water helps them think about the flow of current, that electricity. So again, we did talk about this, where if you're thinking about this as water, the pressure difference is similar to the potential difference in a circuit, and the amount of water that flows past a certain point in a second is similar to the amount of charge that flows past a certain point in a second, which we refer to as the current. So current we defined as the rate at which charge flows. Right? So rate is something over time. We have charge over time, so I equals Q over T, and the unit for this is an ampere. At the bottom of the screen you see a circuit. Now remember, we did briefly talk about the flow of conventional current, which is following the flow of positive charges. That's what you're seeing in this diagram. So you see that arrow at the top that's pointed to the right, so you see the flow in a clockwise direction, but that has gone from the positive side of the battery up to the right and then down through the resistor. We are going to follow the flow of negative charges, those electrons. So that means in this circuit, when we analyze it, the current would flow counterclockwise. Okay, so here again, the current is the same direction as the flow of negative charges for this course. The other thing to remember that helps is that the I, current, stands for the intensity, because again, you will be asked about the brightness of things. That has to do with the current. So we talked about two types of current, AC versus DC, right, or alternating current versus direct current. Right. So again, this is something we talked about. Most of the things that we discuss will be direct current examples. Ohm's law. So this is kind of where we left off, right? We talked about Ohm's law and how Ohm came up with the relationship between current, resistance, and voltage within a circuit. This graph is something really important to know. So when you graph things for circuits, typically it will be the voltage versus the current, where voltage will be on the y-axis, current will be on the x. And when you graph something that obeys Ohm's law, that means that the resistance is constant. So you should get a nice direct relationship here, straight line that you see in the graph that's provided. The slope of this, remember slope is change in y over change in x, so I have voltage over current, which is equal to resistance. So if I asked you for the physical significance of this slope, you would say resistance. This is a graph of a device that obeys Ohm's law, meaning the resistance is constant. It doesn't have a variable resistance. If you had a graph that was curved, that is a device that does not obey Ohm's law because the resistance is changing over time. So resistance is defined as the restriction of electron flow. This comes from interactions at the atomic scale. Right? So electrons move through a conductor, they collide with atoms within that conductor, and they lose some of their energy. And that energy will turn into heat. Okay? So you can think of resistance within the wires or within the circuit itself, but we also talked about how resistance also comes from a resistor, something like a light bulb or a resistor itself, or a hair dryer or your cell phone, right? Something that's going to use the energy. The unit for resistance is the ohm. Electrical power. Right? So we talked about power and energy and work in the very end of our kinematics unit when we were talking about motion. We can also talk about electrical power and energy and work in relation to circuits. Right? So we already learned that power is the rate at which work or energy is done. So this is work over time. Circuits are great examples of this because batteries only last for a certain amount of time. And if you've looked at your parents' energy bill, you know that you are billed for a certain amount of energy that you use in a certain period of time, right, over the course of a month. And this is the power bill. So when we look at power in a circuit, we are looking at the potential difference times the current. So it's interesting to see how certain electrical variables can be used to get the actual power. Right? So you're looking at the potential difference, the voltage, multiplied by how much current is traveling through that. So this relationship, P equals VI, is something important to know. Power, the units here are still watts, and this is on your reference table. Other useful formulas for power, we went through this. So you have useful formulas for power that are given to you on your reference table, and they come from substituting Ohm's law relationships into the power equation. So at the top here you see P equals VI, that's our power relationship, and then under that you see V equals IR, which is Ohm's law. So taking P equals VI and substituting Ohm's law in, you come up with P equals I squared times R, and then at the bottom you'll see a third relationship, P equals V squared over R. All of these are on your reference table. So ways to wire a circuit. This is something that we did briefly talk about in class together. So there's two basic ways to wire a circuit, series and parallel. So in series, you're going to wire things one after another. So you see a series circuit there on the left, where all the light bulbs are one after another in line. The other way to wire a circuit is in parallel, where you have junctions. And you'll see that my light bulbs are actually parallel to one another. They don't follow each other one after the other, but they each have their own branch. Here are your schematic diagrams, schematic symbols that you'll use when you have to draw a schematic diagram of a circuit. And these are also things that you'll see in a few of the different diagrams that will come up dealing with circuits. These are all on your reference table, and you should get in the habit of using them when you draw circuits. Okay. Things to know about some of these devices, particularly the voltmeter and the ammeter. These are special devices that you place in or around your circuit to measure voltage and current. Okay. We did talk about how ammeters need to be connected in series, so right in line, so all of the current flows through it to measure the current. And voltmeters are connected in parallel. The reason for that is voltmeters have a very high resistance. You don't want electrons to actually travel through them. You just want the voltmeter to take a reading of the electron potential at different points. The ammeter has a very low resistance. So when you actually put an ammeter in your circuit, it's not going to change anything about your circuit. It's just going to allow electrons to go through it so it can read the current. So a voltmeter and ammeter, right, just as I talked about here, the voltmeter cannot just be placed anywhere. Right? The ammeter should be placed very specifically depending on what type of circuit you're building and where you want to measure the current. The voltmeter measures the voltage or the potential difference, so it's placed across the device you want to measure, so you can measure the change of that potential. So here's our simple circuit, right? You see lifelike diagrams, and you also see schematic diagrams, both of which you'll need. Here's our series circuit relationships, right? So again, we did talk about this in class together. In series circuit, you have your resistors that are wired one after another. Since they're all part of the same loop, they all experience the same amount of current. Here's our relationships, right? So the current is the same everywhere, and your potential total from the battery will be equal to the sum of your potential drops over each resistor, in this case, each light bulb. The last thing we talked about was the resistance. So as a current goes through a series circuit, the charge must use energy to get through the resistor. So each individual resistor will have its own potential difference. We call this the potential drop because it's taking the energy away. So in a series circuit, we can calculate the total resistance using Ohm's law for each individual resistor, and then we can also use Ohm's law for the circuit as a whole. So in a series, the equivalent resistance is equal to the sum of each of the resistors. Okay. These relationships are all on your reference table. So notice that you will see the word equivalent, in this case effective is also used sometimes. That means total. Right? And again, we stay away from using the word total because in a parallel circuit, it's a little bit different. So here's our example. You have a series circuit that's shown, and there's 4 things that you're asked to find. So I would pause the video, see if you can find each of the 4, and then come back and check your work. So total resistance, 6 ohms. That's the sum of the resistors. Total current, 2 amps, using Ohm's law for the circuit as a whole. Find the current through each resistor. Well, that will also be 2 amps because the current is the same everywhere. And then find the voltage drop across each resistor. So you should get 2 volts for resistor 1, 6 volts for that 3 ohm resistor, and 4 volts for the 2 ohm resistor. Notice that the individual voltage drops, 2 volts, 6 volts, 4 volts, add up to the total of 12. All right, let's talk about a parallel circuit. So you have a wonderful animation here where you have 3 different colors of current. So in a parallel circuit, you have multiple loops, and the current is going to split among the loops with the individual loop currents adding to the total current. So what you see here is the total current that leaves the battery. You have a pink current, a blue current, and a green current. So all 3 of those leave the battery and get to the junction where the green current decides to go through the first light bulb. The rest, the pink and the blue, continue on. At the second junction, the pink and the blue decides to go through the second light bulb. And then the pink continues and goes through the third. At the bottom of that circuit, you see the pink coming over to the left, meeting with the blue current, and they travel together. They meet with the green current, and all the current goes back to the battery. So it's important to understand that parallel circuits have some positions where current splits and some positions where current comes back together. We call these junctions. So in the animation that you're looking at, the current is going to split along the top, right, where the current leaves the battery, and then along the top of that circuit at the top of the screen, you have the splitting junctions where current is breaking off. In this circuit, at the bottom, right, along the bottom of the circuit towards the bottom of the screen is where you have current coming back together. And you'll notice that all of the current that goes into a junction must equal all of the current coming out of a junction. This is conservation of charge, right? Current is the flow of charges, and we know that charge is conserved. So all the current that meets at one point has to equal all of the current that's leaving that point as well. Here's another example, right, of a schematic diagram of a circuit that you may see. So you have the battery at the bottom that short line is the negative side. So electrons are going to leave and go to the right. They're going to go up and they get to a junction, right? This is a combination circuit. So you get to a junction here where some of the current's going to go up and some is going to go down to travel through each of those resistors. And then current's going to meet over on the left-hand side there and travel back to the battery together. Here are my junctions, right? So the junction on the right is where current is going to split, and some's going to go up, some's going to go down. The junction on the left is where current's going to meet and then travel back. Okay, so in a parallel circuit, the total current coming from the battery is equal to the sum of the current going through each branch. And then regarding junctions, current coming into a junction has to equal current coming out of a junction. Okay, so notice that the junctions both touch positive and negative terminals of the battery. Right? So that means in this case, for this particular circuit, you have the same potential difference in each branch. So that means that individual voltage drops are equal. Right? So remember, the battery gives those electrons potential, and they must use all of that potential before they go back to the battery. So in this case, let's say we had a 9-volt battery. Electrons are going to follow the path of those red arrows. At that first junction that touches the negative side of the battery, some current's going to go up through that top resistor. It's only going through one resistor, so it has to use all the potential that it was given from the battery. And then it's going to meet with all the electrons that went through the bottom resistor and go back to the battery. Similar thing occurs if you follow electrons that choose to go through the bottom resistor. They're going to leave the right side of the battery, travel up, get to that first junction. They're going to go down through that resistor. They need to use all of their energy, and then they'll come to the second junction on the right, meet with the current that traveled through the top, and go back. So each voltage drop in a parallel circuit is equal to the voltage of the battery. The resistance is where this gets interesting. So the total or equivalent resistance in a parallel circuit is actually the sum of 1 over each resistor. Right? So the inverse of the equivalent resistance in a parallel circuit is equal to the sum of the inverses of each of the resistors. Okay, so here is an example for you to try. Again, I would pause the video, see if you can work through this on your own, and then come back and check your work. So on the left, you have a parallel circuit, and it's asking part A for the total resistance. Okay, that really should not say total, it should say equivalent resistance, because again, in a parallel circuit, total does not mean just add them up. Right? So we're looking at 1 over 5 plus 1 over 7 plus 1 over 9. That will give you 1 over the equivalent resistance. So you have to take the inverse of that, and you get an equivalent resistance of 2.2 ohms. Now here's something I want you to take note of. Notice that the equivalent resistance of this circuit is less than the smallest resistor. So the smallest resistor here is 5 ohms, and the equivalent resistance is actually smaller than that. That is true of all parallel circuits. The equivalent resistance will always be less than the smallest resistor. Part B, what is the total current? So using Ohm's law for the circuit as a whole, right, I know that the potential of the battery is 8 volts, and I'm going to use the total resistance of the circuit, the equivalent resistance, to give me a current of 3.64 amps. Part C, the voltage across each resistor. Well, since each resistor is its own branch, each voltage drop must be equal to the voltage of the battery. So 8 volts. And then find the current that travels through each branch. So I'm going to use Ohm's law for each resistor. So I get 1.6 amps that goes through the 5 ohm resistor, 1.14 amps that goes through the 7 ohm resistor, and 0.9 amps that goes through the 8 ohm resistor. Again, take note here. More current is traveling through the least resistance resistor. So, current will travel the path of least resistance. Most of the current, or more of the current, will go through the smaller resistor. The resistor with the highest resistance will have the least amount of current traveling through it. And you see that here. 9 ohms only has 0.9 amps. Notice again, the individual currents, 1.6, 1.14, 0.9, add to give me 3.64, which is the total current of that circuit. Complex circuits. Okay, so this is a continuation of talking about series and parallel, and this is where you'll have compound circuits, where you have a series and parallel circuit kind of wired together. So many times you'll see things like this, and so you'll notice we want to find different values here, and I have resistors that are wired differently. So we're going to work from the inside out. So to find the total resistance here, I'm going to look at first looking at my 2 resistors that are wired in parallel. So the 100 ohm resistor is wired in parallel with the 50 ohm resistor. So I'm going to find the equivalent resistance between the 50 and the 100 ohm resistor first. So 1 over 100 plus 1 over 50, take the inverse of that, gives me 33.3 ohms. And I can turn this now into a series circuit. In series, we're just going to add resistors. So I get an equivalent resistance of 113 ohms. Okay, and here's the work for all of that. So now I can use that as my equivalent resistance for the entire circuit and find the potential difference, or the voltage drop, for each resistor, but I can also find the current. So suppose the potential difference is equal to 120 volts. We could find the total current of the circuit. Using Ohm's law, we get 1.06 amps. Okay, so now let's look at the voltage drop across the 80 ohm resistor. Well, the 80 ohm resistor is closest to the battery, and there's no junction between the battery and the 80 ohm resistor. So all of the current is going to travel through that. So I can use Ohm's law with the total current and the resistance of that resistor to get 84.8 volts. Now the other 2 resistors, we need to figure out how much current will travel through them. If we want to do that, we need to know the voltage drop across them first. In order to do that, I need to look at the voltage drop across the 80 ohm resistor. So knowing that the 100 ohm and the 50 ohm resistor are wired in parallel, that means that they are going to have the same potential drop. So we can find that, and then we can find the current through each of them. So again, I recommend that you pause, take a moment to analyze what's going on here, and see if you can get actual values that I've gotten here and make sure our answers match. So the current through the 100 ohm resistor will be 0.352, and the current through the 50 ohm resistor will be 0.704. Notice when I add these together, I get the total current that travels through the 80 ohm resistor, which is the total current of the circuit, 1.06 amps.